In this video, we're going to continue looking at double integrals over non-rectangular regions, and we're going to start out with an example where the region is a type 2. Now, in a type 2, we kind of introduced that idea in the previous video, but let's remember where your y limits are constant and your x limits are, at least one of your x limits would be a variable. So let's start with a sketch so you can visualize that, and then do an example. So in this case, I am going to take, let's take our y equals the square root of x function, but instead of writing y equals the square root of x, I'm going to write it as x equals y squared. So I'm going to write it as x equals y squared. And then I'm going to take the y equals x cubed function, which we have an idea of what that function looks like. But instead of writing it as y equals x cubed, I'm going to write it as x equals the cube root of y, right? So I'm basically expressing the curves x in terms of y as opposed to y in terms of x. But again, we've seen this process in many previous situations. So these are our boundaries. And then with a little bit of algebra, it's not hard to see that these two graphs are going to intersect at 2 points. When x is equal to 0, they both have a y value of 0. So they're going to intersect at the origin. And then also when x is equal to 1, y is equal to 1, so they intersect at the point 1, 1. So let me just do this, skip over here, and make that 1. All right. And where's the region? Well, it's everything between these two. In fact, let me not draw it like this. So since I want to do this as a type 2 integral, remember our y limits would have to be constant. So y will go from 0 to 1. So I'm going to write down that inequality first. So as type 2, or y goes from 0 to 1. That's pretty clear. But now what about our x? We can't say that x goes from 0 to 1 because no, we don't want this part of the region, or we don't want this part, or I should say these parts are not in our region. Our x starts from this curve right here. In fact, let me make this colored right here. And then it stops right there. So depending on which y I pick, notice how long or how short that little line segment was going to be. So if I pick a y close to 0, then that's the line segment. If I pick a y, let's say roughly is approximately a half, then look how long that is. So you can think of what I'm drawing kind of as the width of the region, if you will. And the width of the region varies depending on the y value that I choose. And that's the whole idea of things being non-constant. It depends on your one of your variables, in this case the y. So if you look at these horizontal stripes that I've just painted, if you will, they touch the curve x equals y squared on the left. That's our left boundary. And then they touch again on the other boundary, x equals the cube root of y. So what does that mean? It means our x variable, right? Whenever x is between 0 and 1, y is always between y squared and, I'm sorry, x is always between y squared and the cube root of y. So the y squared becomes the lower limit for x, and the cube root of y becomes the upper limit for x. And these are what we would call like type 2 inequalities that define the region, right? So now, so I've just described the region. So now let me set up the full problem. And the full problem, I have to give you the height now, because this gives us the base of our solid. Now in terms of the height, so I have to give you a z. So I'm going to pick this as my z. Um, Again, not super complicated, but a little bit more involved than the one that we did in the previous video. So here's the equation, the explicit equation for our surface, and we want to find the integral of this function over this. I don't even know how to describe it, right? It doesn't really have a nice geometric name, but it definitely is not a rectangular region. So by definition, this is how we're going to set it up. We're going to do it as a type 2. This is the function that we're going to integrate, 4xy minus y cubed. And since one of our x limits, in fact, both of our x limits are not constant, x is going to be our first variable of integration. So we're going to integrate with respect to x first. The lower limit is y squared. The upper limit is y, and I'll go ahead and write this as y to the 1/3, because we know that that's another way of writing down our cube root. And then for the second integral, we will integrate with respect to y, and we will go from 0 to 1. So there we go. So that's our setup. And I would say in a lot of these problems, the kind of these non-standard, non-rectangular regions, the setup is really key, because procedure-wise now, we do it in an iterative fashion. So we're going to do this integral first. So let me write that one down. Just make it easier to see the process. Oh, that's not where the 2 goes. The 2 goes there. And then we'll have y to the 1/3. And then we have 4xy minus y cubed dx. So since we're integrating with respect to x, y is treated as a constant. Now, we can't factor out a y out of just one integral, because there's only a y here, but then there's a y cubed here. So there are a couple things you could do. You could write it down as like 2 separate integrals, or just keep in mind that we're treating y as a constant. So what we would end up getting is this. So we would have 4y, and then we would integrate the x term, and then that would give us 1/2 x squared. Obviously, there are other ways you can write this, but I just want to show you that the 4y, that multiple doesn't change. The only thing that changes is the x based on our power rule, and then minus, and now the entire y cubed is a constant, so it would be a constant, just think of it times 1, and when we integrate 1 with respect to x, we will end up getting x. So we will have y cubed times x, and then all of this now is going to have to be evaluated at these terms, y squared and y to the 1/3. So let me write it like this. So we'll have y squared, y to the 1/3, right? Okay, now as far as evaluating, if you notice, we can simplify this term just a little bit. When we multiply, we can multiply the constant, so that gives us 2, and I'll just write this kind of alphabetically based on the variables. So then it's x squared y, and then this one is x y cubed. So just kind of rewriting, just to make it as simple as possible before I plug in, especially with the fractional exponent that we have here. So now we're going to plug in, and remember these are x limits, right? So we're going to plug in for x, not doing anything with the y just yet. So start with the y to the 1/3, plug that in for x. We will have 2 times y to the 1/3, all of that squared times y, and then minus y to the 1/3 times y cubed. So all of that is at the upper limit, and then at the lower limit, it's a little bit easier since we're not going to have that fractional exponent. We'll have minus, and then the quantity 2y squared squared times y, and then minus y squared times y cubed. All right, so lots of exponents to simplify now. So we have, for this term, we'll have y to the 2/3 times another y. So adding 2/3 and 1, that gives us 5/3. So this is 2 times y to the 5/3. And again, multiplying these two, you'll have minus y to the 10/3. Again, adding those exponents. So we got that. And then let's distribute the negative and simplify these. Y squared squared is y to the 4th times y, that's y to the 5th. So minus 2y to the 5th. And then finally we have a double negative there, so it's going to be a positive y to the, looks like a y to the 5th. So at least with these are like terms that we can simplify. So here's the simplified result for the first integral. So it's 2y to the 5/3 minus y to the 10/3, and then we end up having minus y to the 5th power. All right. So I would say that's the harder part. That's what we got done. And now we have to do the second integral. And if we go back up, just to remind ourselves what the second pair of limits are, much easier to work with. Y now goes from 0 to 1. So we're going to integrate what we just got here from 0 to 1. So the second integral that we have to do is, let's do, yep, so 2y to the 5/3 minus y to the 10/3 minus y to the 5th dy. So power rule again. So now we're going to add 1. If I add 1 to 5/3, it becomes 8/3. And then dividing by 8/3, I multiply by 3/8. So it looks like this. And then minus, add 1 to this, it becomes 13/3. So that's going to be 3 over 13, y to the 13 thirds. And then a power rule on this, so then minus 1/6 y to the 6th, and all of that is from 0 to 1. So when we plug 1 in, we're just going to be left with those fractions. So let me write down the fraction. So 2 times 3/8, that's 3/4, minus 3 over 13, and then minus 1/6, so we have that. And then at the lower limit now, everything is 0, so minus 0. And if we do our quick arithmetic, and you can double check that 3/4 minus 3/13 minus 1/6, that is equal to 55 over 156 when everything is nice and reduced, right? So that's what it looks like with this double integral over this type 2 region. Notice once we have the integral set up, then the evaluation process, yeah, we have, you know, some power rules and some properties of exponents and all that stuff to utilize, but the process is straightforward. The last thing I'll just mention is, in fact, let me go back up to the region that we started with here. And I just want to show you something, not necessarily to do another example, but I just want to show you that this region, let's see if I can get it all copied here, at least most of it. Whatever I need to fix, I will fix again. This region, I chose to do the problem initially as a type 2 problem, just because I wanted to show you an example of a type 2 problem. And there's our region. So again, let me write down what we just did. So our region as, and I'll put a subscript 2 just for type 2. This would be what it would look like in set builder notation. So it's all ordered pairs, everything there in blue, and they would satisfy these inequalities. So as we said, that x would be between y squared and the cube root of y. And then of course y is between 0 and 1. So that's true. But did we have to do this problem as a type 2 problem? No, we could actually have done this as a type 1. And in order to do that as a type 1, we would have to do two things. Visually, instead of painting the region horizontally, we would have to paint it vertically, which I'm going to do that in a second. And the other thing that we would have to do is we would have to rewrite these equations, right, in the form y equals f of x. So express y as a function of x instead of x as a function of y. So let's actually do that. And I'm going to paste that same region again so you can see it side by side or on top of each other, however it looks. In fact, let me go ahead and make this a little bit smaller so it fits there. Make this one a little bit small. I think that should be fine. So here's what we're going to do. I'm going to erase these equations. I'm going to erase my little bit of paint carefully. Oh, not that. Anyway, I'll draw it back in a second. All right, so again, it's going to be the same region. Right? But let's think about it now. The one that in fact, I just drew back. If I wanted to write y as a function of x, y would be the square root of x. And then if I wanted to write the other equation as y as a function of x, then y would be x cubed, right? And then now here's the key. If I wanted to switch this, and express it as a type 1, I would now have to think of these blue lines. Instead of being horizontal, I would have to do it vertical. And I'd have to say that now x goes from 0 to 1. Because now remember, for a type 1, the x limits would have to be constant. But then and then your y limits would be, at least one of them would have a variable. So it would be like this. So it would look like this. It's just a matter of how do I paint the region. Do I paint the region vertically, which is what I'm doing now, or horizontally as we did earlier? So now let's see if we can write down it's the same region, the same set of ordered pairs, but let's define it as a type 1. So all ordered pairs, and in this case now x goes from 0 to 1. And then y goes from the lower function, the lower of the two functions is x cubed, and up to the larger of the two functions, which is the square root of x. So less than the square root of x. And it looks like that, right? And this process right here, let me write it down. This is basically, and I'll show you why we call it this, and then we'll end. But this process here, you're basically switching the order, or reversing the order of integration. In other words, there are some problems where you could approach it either way, and you could do this. So let me write down the two integrals. So in fact, the one that we did earlier, was this. So using let me just look back up for a second there. Yeah, so y squared to the cube root of y, and then we had our 4xy minus y cubed, and then there we did our x dy. This would be exactly the same if we did it using the type 1 pair of inequalities. Y going from x cubed to the square root of x, the surface stays the same. It's just that now we're changing the order. So now we're first integrating with respect to y, which means we have to use these inequalities, and then the second integral with respect to x from 0 to 1, right? And then again, this is the process now where, now in this case, both ways would work out roughly the same with the same level of algebra, but there are some problems, right, where we actually can't evaluate the integral set up as either a type 1 or a type 2, and we would have to convert it to the other form just in order to do the integration. But this is just an illustration of one, how the process is, again, very similar, but the setup of the double integral is key because then that gives us the path to evaluation. All right, hopefully you found that interesting and useful, and I'll see you in the next video.